Hello everyone again, and welcome to Physics 220 Lab Lectures for Week 4. So this week we are going to work on the roller coaster and its simulations. You're going to start by looking at the CSTR number 4.IP, and the simulation object traverses hills and valleys on a frictionless roller coaster in the realm of zero air resistance. So you're going to be asked to find measurements and make calculations concerning the total mechanical energy and whether it is conserved. Then you'll make some changes to the global air resistance for this simulation and then answer the questions as you did previously. Fill out the data tables and answers and fill in the blanks and send it at the end of the week. So the next thing I want to show you is what these data tables will look like. So notice, again, for Lab 3, this is the answer sheet. There's a ball position, potential energy, kinetic energy, and total energy, or just energy. Remember that potential energy is mgh. Kinetic energy is 1/2 mv squared. Okay, and total energy is just the sum of the two. So notice there's a few different tables, and we're going to do this for some different masses. A 0.01, a 0.1, and talking about whether it's conserved. And then we're going to actually put in air resistance and look at this also. Okay. So now I've actually set up a similar one with an Excel program, so we can actually put these in and calculate these through step by step as we work on the problem. So the next thing I want to do is go over to the actual folders itself and open the interactive. So here's our list of files, and we get for the coaster example, ball on coaster number 4. So we click this and it will open up in our interactive physics. Just apologize for that. And again, just like we've done before, you will notice there are multiple positions, point A, B, C, D, E, and F. And if we let it run through, it's actually going to go really fast. Okay, it'll just zip around, so on and so forth. So we want to reset it, and what you're going to do is you're going to step it through slowly, just like always, and look at specific points. Okay, so what we notice now is, again, we have all these different points for the different energies. So I'm going to reset this. Notice we start at point A, and it has a set potential energy and a set kinetic energy. The total energy will also change as we move through this. Okay, and you can try and pick the different points. So you're going to go and record those for the various points. It's a little ambiguous where you are, maybe at a point B and C and whatnot, especially C. B, D, E, and F are pretty straightforward, but C and A can be a little bit tricky. So then you would go over to the data table. Notice I changed it around a little bit here, and you can get the different balls positions, and you can literally just call them A, B, C, D, E, and F. It's just the points. And then fill the different energies. And what you're looking to see, as almost a kind of check, is the total energy conserved or not? Okay. And notice this starts at a default value of 0.1 kilograms. So let me actually kind of run through one of these. If I can go back to A, we'll start with the reset. So notice I put A, and there's the kinetic, potential, and total energy. So I come over here, and I can put 0.06 in the potential, 0 for the kinetic. And if you notice, the total energy is also given as 0.6. Okay, and this is actually just for the mass, 0.01. That's not actually a value we actually want to deal with. Now, if we let it traverse to point B, let's see if I can do it kind of fast. Not too great. Then we can continue on, and now point B, kinetic energy is potential energy is 0.05, kinetic energy is 0.55, and you should see again that now the total energy should be the sum of that, which is 0.6. Now we can continue on with that, and I'll actually fill this out, and you guys can watch me, and we're going to then be able to look at the questions and see what's of interest here as we work on these for this first part of the lab. So we have point B, so I'm just going to move over to C. Again, it's a little bit ambiguous here where C is. Potential energy is 0.25, kinetics 0.35, and again this is 0.6. And as we were going to step through this, we can see some of the different values. You should notice a trend for all the different points, and then you should be able to go over to the lab worksheet and answer the questions. Is total energy conserved within the experimental area? If yes or no, where did the energy go? So now the next step we want to do is change the mass of the ball for our next experiment, where we're going to run this through at 1 kilogram and see if there are any differences. So now we want to run through the example where we actually go and look at a situation where we're looking at a mass of 1 kilogram instead of 1.1. So this is our basic. We start with a 0.1. It's a little interesting how you do it. You actually have to change, you go into world and you actually have to change the gravity. So you literally make the gravity 10 times stronger to simulate an example where it's going to be a 1 kilogram instead of a 1.1. And always move it forward a little bit and then move it back. And what you notice is that the values should jump up by about a factor of 10. If you let it run through the full simulation, you'll notice it goes quite quickly and moves back and forth. And the one thing you'll notice is it kind of keeps going forever, which is what you would expect. I'm going to reset this and then step it through. And again, you look at our different values. It'll go much quicker. Then we get down to B, and we can calculate the different values at the different points, like we have set up on the graphs here. And again, you can put your ball positions, and you just copy them over to make your life easier. A, B, C, D, E, F. Again, the potential energy, the kinetic energy, and then the total energy at that point for the one of the values in particular. And again, like I said, to point out is if you let this run, notice it will kind of go back and forth together, because one of the things we've done here is we set up a situation where there is no air resistance or no gravity involved at all, so that the problem can basically run almost infinitely long until we want to actually go back and look at a specific point. So I want to look at point F in consideration here. And actually see if we can get it over there at some point and see what it looks like up there. Notice it doesn't quite actually go back up. Actually, if we reset this, it more than likely will. So we actually have to move backwards up and see where it actually goes at this point. And we can actually get a good determination of the measurements and the values and what we want to actually work through at this point. Okay, so let's go back, change our gravity back to where it does, yes, and you have to reset every time you change the world. Click yes, and then reset, sorry. Put the gravity back down to where it was, so this is like a 0.1. And the next thing we want to do is change the air resistance of this. Okay, so we want to change the air resistance here to see how it works. So again, we go up to world, air resistance, and you notice it just gives you none, which is what we had been working with, low speed and high speed. We want to work with low speed because that means it's proportional to the velocity. High speed, it's proportional to the square of the velocity, which is things like jet planes and things like that. Notice that the evolved is 0.05 kilogram meter per second, which is what we want. If you go over here, notice that's what it says. Change from 0 to 0.5 on the world menu. So we click OK. And I would just want to run through this and let this go, and you'll notice something right away. If there's air resistance involved here, it's not even going to make it to some. So we can reset that and look again. And notice it doesn't even barely make it to C, and it's definitely not going to make it to D at the point. So if we reset this, you really need to step this through to each one. Again, go back at the point and see what the value is. And by the way, when it has a number like that, 8 times 10 to the minus 3, that basically means 0. And again, notice what the potential energy is. And as we step it through, we can even go and kind of pause it around to that point. There it is at point B. But if we back up, notice it will barely make it up to point C. And then we can get our values. And notice what happens to the total energy. Remember where it was when it started. It was at 0.6. Now it's gone down to the VAT value. So by looking at this and being able to adjust the parameters, Play with the mass, which we kind of have to do through the acceleration. Play with the air resistance and see how this ties in. We can get a better understanding how a real physical example plays through. You're going to go over here and fill out the data tables in question. Determine whether the total energy is conserved for each case. If no, where did it go? And then tie it in, look for a nice, neat solution, and finish up your lab for the week. Remember, if you have any questions at any time, just email your professor, and they will do all they can to get back to you, and hopefully you can have a nice, good lab experience for the week.